now we discuss vibrational partition function. Which we define as Q vibrational. For this, we consider again the simplest model like harmonic oscillator model. So, we consider simple harmonic oscillator model. So, Q vibrational we can write like V goes from 0 to infinity e to the minus beta epsilon vibrational, where epsilon vibrational is V plus half h times nu. Nu is the frequency, V is the different vibration levels, and V goes from 0, 1, 2, etc. H is Planck's constant. Okay. And nu can be written as 1 by 2 pi root over k by mu, where k is the bond force constant and mu is the reduced mass of the molecule. Okay, so, if we substitute the expression for vibrational energy into the partition function expression, we get Q vibrational is minus beta times V plus half times h nu. Okay. Now, we can further simplify this equation like you can take out e to the minus beta h nu by 2, and inside the summation now we have V goes from 0 to infinity e to the minus beta V h and nu. So, you get Q vibrational is e to the minus beta h nu by 2. Now, if we expand it, we get 1 plus e to the minus beta h nu plus e to the minus 2 beta h nu plus, and it goes on. So, if we consider e to the minus beta h nu is x, then we can write 1 plus e to the minus beta h nu plus e to the minus 2 beta h nu like this as 1 plus x to the 2 plus x to the 3 and so on. So, we get 1 by 1 minus x, provided or if x is much lower than 1. Okay. So, we can write Q vibrational as, so Q vibrational is e to the minus beta h nu by 2, and in the denominator we have 1 minus e to the minus beta h nu. So, this is the partition function. This is the partition function for vibrational. This is the vibrational partition function. Now, assume or consider theta vibrational is h nu by kb. where theta vibrational, like the case for rotational partition function, here theta vibrational is the vibrational temperature. And it has temperature unit. Okay. So, now if we substitute theta vibrational into the expression of Q vibrational, we get Q vibrational is this. Q vibrational is e to the minus theta vibrational by 2 times t, and in the denominator we have 1 minus e to the minus theta vibrational by t. So, we have got the partition function or vibrational partition function. Now, we can calculate the average vibrational energy of a single harmonic oscillator. So, next we calculate average vibrational energy of a single harmonic oscillator. We know how to calculate average energy. The average energy or average vibrational energy of a single harmonic oscillator we can write like Kb t to the 2 del ln q vibrational by del t, constant, or you can write like minus del ln q vibrational by del beta at constant volume. And we have the expression for vibrational partition function. Q vibrational is e to the, so we have Q vibrational is e to the minus theta vibrational by 2t by 1 minus e to the minus theta vibrational by t. If you take log both sides, we get so if we take log both sides, we get minus theta vibrational by t minus ln 1 minus e to the minus theta vibrational by t. So, we can write del ln q. Now, if we do the differentiation with respect to temperature of ln q vibrational, we get, for the first term we get q vibrational by t to the 2. For the second term, if we do the differentiation with respect to temperature, we get this term. So, if you further simplify, we get, and if we substitute the value of del ln q vibrational by del t, then we get epsilon vibrational is Kb times theta vibrational by 2 plus theta vibrational by e to the theta vibrational by t minus 1. So, this is the expression for vibrational average vibrational energy of a single harmonic oscillator. Okay. So, if we have n number of such harmonic oscillator, so if we have n number of such harmonic oscillator, n number of harmonic oscillators in the system, then the average vibrational energy of the system is n kb and we know n equals to small n times Na, where Na is the Avogadro's number. So, if we substitute that here, we get so this is the average vibrational energy of a system having n number of harmonic oscillators. So, we get average vibrational energy. Now, we can calculate CV for vibrational degrees of freedom is nothing but and if we do it, we get so this is the expression for CV for vibrational degrees of freedom is R theta vibrational by T to the 2 e to the minus theta vibrational by T. In the denominator we have 1 minus e to the minus theta vibrational by T to the 2. Okay. Next we calculate the fraction of molecules in the with vibrational energy level. And that is if V is e to the minus beta h nu V plus half by Q vibrational, right. So, this is the general expression for fraction of molecules in a given in a particular energy level. So, if we substitute the value of QV, we get if V is 1 minus e to the minus theta vibrational by T times e to the minus V theta vibrational by T. So, this is the expression for fraction of molecules in the with vibrational energy level. Next, what we do, we will consider one example, numerical example, and to see what is the fraction of molecules in a particular vibrational energy level. So, one example is calculate the fraction of N2 gas molecules in the V equals to 0 and V equals to 1 vibrational states at 300 Kelvin temperature. So, this is a numerical problem. Consider theta vibrational is 3374 Kelvin. Theta vibrational for N2. So, theta vibrational for N2 is 33. N2 gas molecule is 3374 Kelvin. Okay, so we calculate e to the minus theta vibrational by T is e to the minus 3374 Kelvin by 300 Kelvin. It gives us e to the minus 11.25, and this gives you 1.31 times 10 to the minus 5. Okay. So, what is F0? Means when for V equals to 0 state, the fraction of molecules, if we consider F0 or F naught, we get e to the minus 1 minus e to the minus theta vibrational by T. So, we get the value is 1 minus 1.31 times 10 to the minus 5 gives you close to 1 value. Okay. So, almost all molecules are present in V equals to 0 state. And what about for V equals to 1 state? If we consider the fraction of molecules in V equals to 1 state as F1, we get 1 minus e to the minus theta vibrational by T times e to the minus theta vibrational by T. So, you get 1.31 times 10 to the minus 5. So, at room temperature or at ordinary temperature 300 Kelvin, almost all molecules are in the ground vibrational level. So, if we plot in general, if we plot a V versus V, so what I said is in general most molecules are in the ground vibrational state at room temperature. At room temperature. So, if we plot a V versus V, so this is V equals to 0 state, this is V equals to 1 state, this is V equals to 2 state, and so on. So, this is your close to 1 here, and then you have most of the particles here, very less particle here. So, it decreases almost exponentially. Okay. So, exponential decay we are observing here. So, that is all about vibrational partition function. Next, so far we have considered canonical ensemble. For canonical ensemble, we know number of particle, volume of the system, and temperature. These three quantities are fixed. Now, we consider another ensemble, which is known as grand canonical ensemble. And for grand canonical ensemble, volume is fixed, temperature is fixed, and chemical potential is fixed. So, number of molecules can vary from one state to another state. Okay. So, we will start now grand canonical ensemble. So, as I mentioned, in grand canonical ensemble, mu v t fixed. Okay. Mu is the chemical potential, V is the volume, and T is absolute temperature. So, these three quantities are fixed. So, we can represent grand canonical ensemble like if we draw a diagram like this. So, here mu Vt fixed, etc. Okay, so this is the thermal insulation. And this is the system. These are all, they all represent system. And through this wall, so these walls are both heat conducting and permeable to the passage of molecules. Okay, so, through this wall both heat and matter exchange are possible. So, they typically represent, or this grand canonical ensemble is applicable for open kind of system. Okay. And the whole thing is isolated from surroundings. Now, in grand canonical ensemble, as I mentioned, in grand canonical ensemble, mu Vt fixed, right. If there is more than one component in the system, then the chemical potential mu, chemical potential mu of each component is the same from system to system. Like we did for canonical ensemble, here we define one quantity ANJ Remember, we defined a quantity Aj in canonical ensemble. Here we define a quantity Anj. Anj represents the number of systems in the ensemble that contains n molecules are in the state J, in which the energy is E n j. So, A n j represents the number of systems in the ensemble that contains n molecules and they are in the state J in which the energy is E n j. Okay. So, this A n j, it is a function of n or number of molecules n, unlike canonical ensemble. As n change or number of molecule change is permissible. So, we can write sum over n, sum over j, A n j is A, where A is the total number of system in the ensemble, total number of systems in the ensemble. And so, this is our constant 1, and sum over n, sum over j, A n j times E n j gives total energy of the ensemble, which is also fixed. This is our constant number 2, and we have sum over n, sum over j, A n j times n j gives n. This is total number of particles or total number of molecules in the ensemble. This is constant number 3. So, we have sum over n, sum over j, A n j equals to A, which is fixed. This total number of system in the ensemble is fixed. Total energy of the ensemble is also fixed, and total number of molecules in the ensemble is also fixed. Though energy can be exchanged between the systems and number of particles can be exchanged between systems, but total energy of the ensemble is fixed and total number of molecules in the ensemble is fixed. So, we have 3 constants in case of grand canonical ensemble. Remember, if you go back and check, for canonical ensemble we have 2 constants. Okay, so, for any possible distribution like we did for canonical ensemble, here we are also calculating the possible distributions. So, for any possible distribution the number of states is given by if we say number of states W, we get okay. So, we get A factorial and in the denominator we have product n and j, A n j factorial. So, this is our suppose expression number 4 and this W is the for any possible distribution number of states. Okay. So, as in the treatment as we did for canonical ensemble, the distribution the distribution that maximizes W subject to the condition or subject to the appropriate constraints. So, we have 3 constraints here. So, if we maximize, if we maximize W, so if we maximize W of equation 4, under the constraints mentioned above. So, the 3 constraints we just mentioned above. So, if we maximize W under these constraints, we get e to the minus alpha, e to the minus beta e n j and e to the minus gamma n. If you go back and check for canonical ensemble, we had alpha and beta 2 Lagrange multipliers because we had 2 constraints there. Here we are having 3 constraints. So, we are having alpha, beta and gamma, these 3 terms. Now, we can calculate e to the what is the value of e to the minus alpha like before. So, if we do sum over n, sum over j, n j, we get total number of particles, total number of systems in the ensemble is nothing but we get e to the minus alpha sum over n, sum over j So, we get e to the minus alpha is a by sum over n, sum over j, e to the minus beta e n j and e to the minus gamma n. Now, if we substitute the value of e to the minus alpha into the expression of a n j, we get thus a n j is a by A by sum over n sum over j e to the minus minus beta e n j e to the minus gamma n, and then in the numerator we have e to the minus beta e n j times e to the minus beta e n j and e to the minus gamma n. So, we get p n j, which is function of v t and gamma is nothing but a n j by a, and you can write e to the minus beta e n j and e to the minus gamma n by sum over n sum over j e to the minus beta e n j to the minus gamma n. So, this is the probability of finding a system having n number of particles and in the state j having energy E j, right. So, we get P n j is e to the minus beta e n j function of volume e to the minus gamma n by theta is function of v, t and gamma, where capital theta is sum over n sum over j e to the minus beta e n j by e to the minus beta e n j and e to the minus gamma n. This capital theta is known as grand canonical partition function. Okay. And here, which is a function, this grand canonical partition function is function of v, function of t and gamma, and if you remember that we considered for grand canonical ensemble v, t and mu are constants. So, gamma is related to mu chemical potential mu, that we will see later. Thank you.